Hi, folks, and welcome back to Physics with Captain Rod. I'm making this video here to help you out with number 20 in your homework, which is essentially the same problem as 19, just different questions. So this helicopter blade, right, starts from rest, and then the person, turns the motor on, if you will, and this blade starts rotating, right? So it's got an angular velocity now. And if you were to sketch angular velocity against time, I have a graph that looks maybe something like this, assuming a constant angular acceleration. Now, if we pick a point on the end of the blade here, right, that point is moving faster and faster and faster as the rotation rate increases. If we were to sketch the speed, which is the magnitude of your velocity against time, that too would look something like this. And the tangential acceleration, this is the same acceleration we've been talking about most of the class here. It's the acceleration that's tangent to the velocity. And when you calculate it, it's actually equal to a change in speed over a change in time. You can actually calculate it like that. So on this graph here, again, that's slope, just like always. The change in speed is this distance in the graph, and the change in time is this distance. Now, the change in time is given. This is what you have to figure out, right? What is this value? And to know that, you need the final speed. Like, what is that? So let's talk about this 400 RPM. At this instant in time right here, that is the angular speed of the blade in revolution per minute. You can calculate the linear speed by this way. The speed, which is the magnitude of v, remember, is distance over time. And just for a moment, we're going to pretend like the 400 RPM is constant. And what you can do is then take your 60-second time frame, and then the distance traveled would then be 400 times the circumference. And whether the speed were constant like this on the graph or increasing does not matter here. That doesn't make any difference at all. So you can calculate the speed just like you would before. And then that's this distance on the graph here. And then divide by time, there's your tangential acceleration. Moving along here, let's see. Centripetal acceleration of the tip at full speed. So once you have this value, remember that centripetal acceleration is equal to v squared over r. And that's just going to be a, put in the number and calculate. Now, you're going to get a really, really large number. Centripetal accelerations very quickly become the dominant accelerations in rotation problems. So don't be too shocked if you get a massive number when you calculate this centripetal acceleration. Okay, so what is the centripetal acceleration of the tip at t equals 1 second? So again, centripetal acceleration is equal to v squared over r. So what you need is v of 1. You need the velocity at 1 second. So if you go back to that, I'll call it speed graph, magnitude of your velocity. That's really what you need. I keep saying velocity, but really you need speed. Remember, it started from rest, right? At t equals 0, the blade is not moving yet, the tip or anything. Sometime later, given in the problem, it is moving. This is now a value you would know from above. We'll make our constant acceleration assumption. Now what we need, right, so this time, I forget what it was in the problem, but something like 6 or 8, or maybe I should look. All right. 12 seconds. So there's a couple ways we can kind of proceed to get the speed at 1 second. So 1 second's like here on the graph, kind of exaggerated. And I'll talk about two different methods. The acceleration, once you know that, is change in velocity over change in time. This is the slope of this graph. And it's equal to the v final that we calculated earlier over the delta t of, I think it was 12 seconds. But it's also equal to a change in v over change in t using these 2 points, where the change in t is 1 second. Then you can get your change in v and then calculate your centripetal acceleration. The other thing you could do is we could say, okay, well, this is a linear function, so it has to look like v equals a number times t, and that number is the acceleration, which I think you found previously. And then put in the 1 second to get your speed and into your centripetal acceleration at 1 second. So hopefully that'll get you through that problem. Have a great day.